Good afternoon, everybody. We're going to try to start on time so we can keep track of time and we don't go very late. I am Pavlos Protopapas. I'm Scientific Program Director for the Institute, and I'm going to chair the second session, which is about data analysis in data science. We have 3 talks, and we're starting with Cynthia Rudin, who is a professor of statistics at MIT. She got her PhD in applied and computational mathematics from Princeton University. Her work appeared in Business Week, Wall Street Journal, the Boston Globe, and many other journals. And her title of her talk is Machine Learning for the Future of Healthcare, Energy, and the Internet. Thank you.
Okay, great. Great, so yeah, I'm talking about 3 applications of machine learning to what I think of are 3 of society's critical problems right now: energy grid reliability, web search and information retrieval, and personalized medicine. So I'm going to start with energy grid reliability. So I've been working on this topic for about 7 or 8 years now with the power company in New York City. Okay, so most people understand that the electrical grid needs to be reliable, right? We know that. But what most people don't know is that the electrical infrastructure in many places is very old. Some parts of it are about 130 years old from when electrical grids were first introduced into the world. And New York City's grid is the oldest power system in the world. It dates from the 1880s. And there are still cables in the ground from the 1890s, actually from the time of Thomas Edison. And our group calculated that over 5% of Manhattan's low-voltage cable was installed before 1930. But not only is the grid old, it's also very, very large. So just in the little tiny island of Manhattan, there's almost enough underground electrical cable to go all the way around the world. Now, this is the Department of Energy's Grid 2030 document, which outlines our national vision for electricity. And the first major finding in the executive summary section of the document is that America's electric system, the supreme engineering achievement of the 20th century, is aging, inefficient, and congested, and incapable of meeting our future energy needs. But as I mentioned, it's very difficult to just sort of upgrade to a smarter grid, right? Because the grid is absolutely massive. So what a lot of power companies are thinking about doing or have started doing are these maintenance programs, these proactive maintenance programs or inspection programs, where they use historical records of past failures to try to predict future ones, and then do the maintenance work before the failure happens. And this is something that's new for them, because in the past, they did mainly reactive maintenance, where if there was a problem, they would go and send somebody to fix it. So this prediction step, that's something that's new for them. Now, what all these companies have started doing is inspection programs where they inspect the access points to the underground electrical grid. So every city in the world that has an underground electrical grid has these manholes. These are holes in the ground, and these are access points to the underground grid. So right now, you can kind of see where the electrical cables go underneath the ground, because you can see this line of manholes there. And so these inspection programs, they inspect all these manholes. And if there's a problem in the underground electrical grid, like a really serious problem, you'll see it in a manhole. And what you might see is something like this, like a fire or an explosion or a smoking manhole. And these kinds of events, these are almost always due to insulation breakdown of the low-voltage cables within the manholes. And being able to predict these kinds of events can lead to an improvement in reliability of electrical service. It can help public safety, and it can save the cost of repairing a lot of damage that you can imagine would be caused by one of these underground events. Okay, so these kinds of things are not too far away from home. So this one happened almost a year ago here. This one I remember very clearly because I was giving a talk about electrical reliability at the time, and the power went out, and the whole audience was sitting in the dark, and we actually had to stop the talk, and everyone had to leave. Okay, so I've been working with this power company in New York City for 7 or 8 years, and we have data from all over the company. We have data about the manholes themselves, where they're located, whether they're a manhole or a service box. We have data about the whole underground electrical grid, the cables that connect every manhole to another manhole, main cables or service cables that connect manhole to buildings. We have data from their inspections program, which again is relatively new. It's about 10 years old. And we have data about past events. So we're trying to predict manhole events, right? Fires and explosions and smoking manholes. So the event data is our most important data. And so the idea is this. When you have some kind of problem, like your lights are flickering or your lights go out, you call up a Con Edison dispatcher, and they start typing in a trouble ticket while they're directing the action of what to do about it. And we have hundreds of thousands of these trouble tickets. And this is an example of one of these tickets. And if you're sitting close enough and you're trying to read it, you're going to have some trouble because it's very, very difficult to read. You can see there's a lot of misspellings, a lot of irregularities. Not all the information pertains to predicting manhole events, right? These data were not designed for that. It's just record keeping here. So for instance, there are at least 38 variations of service box, which is an important term for us. And these are all variations of the word barricaded. So these are the kind of issues that make it very difficult to take these data and put them in a database and process them and get something that resembles a predictive model for electrical grid reliability. Okay, so we've had some level of success with this. So this project is a challenging project that incorporates historical, diverse, and heterogeneous data sources. And a major theme of this project is repurposing data tombs for prediction, right? No one would have thought when they're creating these trouble tickets that these were going to be used for predictive modeling, right? They were not designed for that purpose. It was, when we started it was a high-risk project because it was previously unknown whether power grid failures could be predicted at all because of the barrier to working with this kind of data. So, like I said, we've had some success in being able to do this, and we've quantified the amount that we're able to do the predictions. But what I want to do now is, I want to point out that this is the tip of the iceberg, right? We're not there yet. And I want to tell you a little bit about our new statistical tool that we think is, this is where we're at right now. So this is a statistical model called reactive point processes. It's new. It aims to answer what we consider the holy grail of manhole event prediction, which is short-term or even real-time event predictions. This is something we really didn't think we could do when we started this project. And it's a generative model for the past, and we can use it to simulate the future and test inspection policies to tell Con Edison, okay, which inspection policies will produce which kind of results. And the idea is that it has self-exciting components, self-regulating components, and saturating elements that I'll tell you about in a minute. And it's a very general marked point process model. So here's how the model works. So each manhole has a baseline vulnerability level. And then if a manhole event happens, like flickering lights or a smoking manhole or something like that, then it indicates that there's some sort of weakness in the general area, there's some infrastructure problem. And so what happens is there's a spike in vulnerability, and that spike, it's a spike in vulnerability to future events. And if nothing else happens, it gradually decays back to the baseline level. And then if an inspection happens with a repair, then the manhole's vulnerability level decreases. And then if nothing else happens, as things kind of settle and there's more, snow gets into the manhole and all kinds of stuff, the effect of the repair wears off and it goes back to the baseline level. Okay, so there's self-exciting, there's the self-exciting component, the self-regulating component, and then there's this saturation component that I haven't told you about, which is the effect of diminishing returns. But if you inspect a manhole a whole bunch of times in a row, that's not going to be the same thing as inspecting it once, right? There's diminishing returns of the umpteenth time you've inspected the manhole. So this is the form of the model, and what it is so G2, that function G2 there, that's my self-exciting function. That's the one that goes up and then down. And then the self-regulating function is G4, and that's the one that goes down and then up. And G1 and G3 are these sort of diminishing return functions that sort of, saturate. And then the last thing is this baseline adjustment. So if the manhole has ever had a manhole event in the past, then its baseline vulnerability level just hops up a notch. It hops up by C1. And the nice thing about this model is that it fits the Manhattan data beautifully. So each of these blue dots represents a bunch of time intervals of different manholes in Manhattan. And so that's the blue dots are just directly from the data. And then the red curve is our fit to the blue dots. Okay, and this is the self-exciting function. That's the G2 function that goes up and then down. And then this is the saturating function. And you can see, so the blue dots, again, are data derived from here. And then the red curve is our fit to those blue dots. And the point is, that's not exactly a straight line. There's some saturation going on from diminishing returns. And then this just is meant to show you that both of these curves can be described by a one parameter family of functions. So it's a very, very simple model in the sense that there's only like one parameter governing this, but it's the best thing we have out there to model manhole events and predict manhole events. And what we decided to do after that was to try to personalize the model so that each manhole gets its own decay rate. And we did that using a regression model, and we used some statistical tools to fit the coefficients. And as I mentioned, it's currently the best tool we have out there for predicting power failures in New York City, and it beats all the baselines that we've derived. But as I said, this is not the be-all and end-all, right? This is the tip of the iceberg, and there's a lot of work that could be potentially done in this. And even if you can increase your predictive power a little bit, it could have a very big effect. So for instance, if you can even reduce the number of manhole events by 1, it could save quite a lot. So this paper, what they did was they estimated the true cost of one particularly bad power outage in 2003. And they estimated that cost at $1.05 billion and 90 lives. So that's why this is an important problem. That's why we should continue to try to solve it. So the next application I want to discuss is an information retrieval application, growing a list using the internet. So in my view, the current generation of search engines tells you where to find the information, but the next generation finds it for you. It goes to the websites, reads the websites, brings back the information you need, and finds it for you. So we've been trying to build one of these next generation search engines, and the idea is that it can grow a list of almost anything starting from a seed. So you give it a seed of a couple of things that you care about, maybe like politicians or something, and then it grows more. It just looks at the internet. The internet's the database, goes to the internet, finds more. And we designed it to have some certain specifications. It's got to be automated. It should be similar to Google Sets and Buwa, which are our competitors. So Google Sets is a Google product. And it's available on Google Spreadsheet. And Buwa is an academic engine. And so it has certain specifications. We wanted it to be a production quality thing, right? It had to be fast. Everything it does has to be efficient, use efficient subroutines. It should piggyback off the fact that we can already solve search, right? We already have search engines, so we want to use those as subroutines. And everything has to be able to be made parallel, right? It has to be something that, say, Google, if they wanted to, could implement in a second. So I want to show you some just a couple of results from this new search engine. We did a search for events in Boston. So we wanted yearly events in Boston. And we started with the Boston Arts Festival and the Boston Harbor Fest. And so we put those into our new search engine, clicked go. It came up with 3,090 potential events in Boston. And I want to show you the top of the list here. So the left column is the top of that list. And then over here, I have the source, the web page where we got the information. You can see there's a variety of sources. So here's like a news website, telegraph.co.uk. We have celebrateboston.com, so places where you'd put Boston events, soulofamerica.com, sort of all over the internet. And you can see that we came up with pretty much all Boston events, right? Not everything, but most of it. So for example, First Night Boston, or the Chinatown Main Street Festival, the Berkeley Beantown Jazz Festival, you know, whatever. It's events in Boston. And these are the results from our competitors. And you can look at the Google Sets results if you like. I will admit that the Google Sets results does contain one event that did happen in Boston, which is the Boston Massacre. It's not a yearly event. It's not what we were kind of looking for, but luckily it's not a yearly event. Anyway, the BUA results are a little bit better, but it still has a lot of junk over here. This whole thing is junk. Okay, so the second experiment that we did is Jewish foods. And Jewish foods is a very broad experiment because there are all different kinds of people on the internet who know about Jewish foods. And we're getting information from, HungarianKosher.com and eCampus.com, restaurant websites and menus and all kinds of stuff. And from all over the world, too. So we seeded it with challah and knishes, which I think of as quintessential Jewish foods. And it came up with potato latkes and blintzes and noodle kugel and simmies and matzo balls and stuff like that. So that's great. So let me show you Google Sets and BUA on the same problem. And I particularly like the Google Sets results. I love the lovely Jewish tarta de asparagus and leftover meat casserole, the beautiful Jewish chicken quesadillas, whatever. So BUA, again, is a little bit better, but still not the same quality. It still has things like shop online and so on and so forth toward the top of their list. So that's just a taste. So we have a paper where we quantify the quality of the results, but you get the idea. So just to summarize for growing the list, the next generation of search engines is possibly closer than it seems. Okay, so now on to the third application, which is personalized medicine and interpretable predictive modeling. And those two topics go hand in hand. And why is that? It's because doctors insist on using interpretable models very, very often. So this is the coronary heart disease score sheet for men. So if you're a man, you go into the doctors, and they ask you 5 questions. They say, how old are you? What's your cholesterol level? Do you smoke? And so on and so forth. And you get a certain number of points for each answer that you give. And then they add up all the points, and that translates into your 10-year risk of coronary heart disease. And that's great, but where did they come up with those 5 questions, and where did they come up with those point values? And the answer is they made it up. I mean, you could actually, right? Why would I ask those 5 questions? There's a huge amount of information we're keeping track of about each person. Why would we only use those 5? So what I've been trying to do is produce predictive models that are both accurate and interpretable. And accuracy, we know what accuracy is in machine learning. We know how to measure accuracy. But interpretability is inherently subjective. So when I say interpretability, I mean models that are concise. They've got to be short, like I only want to ask people a few questions. And they have to be convincing. I want to be able to give a statistic behind each prediction that I make. And then the thing is, so there's always been this question of whether you need to trade off interpretability to get better accuracy or vice versa. And I actually am not convinced that you need to make a sacrifice here. In fact, I've been working under the hypothesis that many real data sets permit powerful predictive models that can be surprisingly small. And I've seen this over and over again. So this is an example of the type of model that I would like to construct. Okay, this is called a decision list or an associative classifier. And here is an example of one, and it's trying to predict whether I'm going to get stuck in traffic on my way home today. And what it does is it says, all right, is there a game at Fenway Park? If there's a game at Fenway Park, then I predict I'm going to get stuck in traffic. Right? And I know that because 97 out of the 100 times there was a game at Fenway Park, I got stuck in traffic. Okay, so if there's not a game at Fenway Park, I look at if it's rush hour. If it's not rush hour, I'm going to predict no traffic, and there's the statistic for that. And then else if there's no rain and no construction, no traffic, or Friday, no traffic, and so on and so forth. So that's the kind of model I want to construct, very interpretable. And I want to keep it concise. I want the number of elements in the list to be small, right? These are rules. Each line of this decision list has an if-then rule in it. I want the number of rules to be small. I want the size of the rules to be small. I want the total number of conditions to be small. And there's a lot of precedence for this form of model in the artificial intelligence literature because, in fact, it's in the same form as the knowledge base in the expert systems literature. Now, if you think about the top 10 algorithms in data mining, very few of them produce interpretable predictive models. Only 2, CART and C4.5. And these are decision tree methods that they're very greedy. They start from the top down, and they look at one kind of feature at a time, and then they go back and prune. They're not truly optimized for either accuracy or interpretability, but the main reason they're famous is because they are both accurate and somewhat interpretable, right? So what we want to do is we want to kind of beat decision trees. So I've been using this framework that comes from the associative classification literature, where you do the following. You take your database and you mine it. You throw a whole lot of, you get a rule mining algorithm. There's a ton of these things. They're all over the place. We've been working on this problem for 10 years to find great association rules from data. So you throw one of these algorithms at it, and you get a giant pile of rules. So if-then rules. Then you take the rules, and you figure out how to order them to produce a very accurate but very interpretable decision list. And that's the key step, because as long as you've mined enough rules in the first step, you can rely on that second step to do the modeling for you, right? Because you need that first step, because otherwise the computation is a beast, right? It's terrible. But if you can just get through that first step, and then that sort of narrows your space well enough so that you can order the rules into this nice list. So we designed a model called the Bayesian list machine, which is now won 2 data mining contests. And the idea is that it's just black box classification. Okay, so you just give it X's and Y's, and it takes all of your data, throws a rule mining algorithm at it, gets a pile of rules, and orders it according to this probabilistic model of permutations of rules. So it permutes the rules in a nice way. And it uses the Bayesian prior to gain interpretability. It uses a prior as a tool to kind of force the model to be small. It's got to be concise both in this direction and in this direction. It's got to be concise in the number of rules and in the number of conditions in each rule. And so the prior looks something like this. So that R pi term, that is the number of rules in the list. Okay, so we want it to trade off with also the size of the rules, which is that other term over there. So that constant C trades off between whether we want a small list this way and a small list that way. And we insist on both of those things. And then P is just the strength of that prior. And the code for this, by the way, is publicly available, so you could try it out if you want. And so what we decided to do was to use this tool to design a better Chads2 score. So the Chads2 score is used in every hospital in the country to measure stroke risk among patients with atrial fibrillation, because those patients are particularly vulnerable to stroke. Now, the Chads2 score is a medical scoring system. It was developed using data from less than 2,000 patients, and it considered only 5 things. They asked people only 5 questions, right? They had 5 things. And then the number of people who had the maximum score was about 5. So in other words, they had a small sample problem at the top end. So for us, we started with 11.1 million patients, and we took those that had atrial fibrillation, and we had a year of observation time kind of before and after their diagnosis. So we just took patients that we had enough observation time around. And that left us with 12,500 patients. That's not 1,733 patients. That's 12,500 patients. And we considered all drugs and conditions, whereas they considered 5 things. We considered all drugs, all conditions. So this is over 1,000 times the amount of data that they originally used. And we built this. This is our new Chads2 score. And as you can see, it's quite simple in the sense that it fits on half the slide. And let me tell you what it says. So it says that if you had that top one, is what it means is it's a stroke causing paralysis, a very serious stroke. If you recently had a very serious stroke, then you have a 58% chance of having another stroke within the next year. If that didn't happen, if you had a prior stroke, then your stroke risk is 46.6%. So not a very serious stroke, but a less serious stroke. Or, and if you didn't have that, if you had TIA, which are mini strokes, and hypertension, which is high blood pressure, so the blood flow to part of the brain stops briefly there. And then your stroke risk lowers again. So the more serious strokes you've had in the past, that increases your risk of stroke in the future. And then there's a couple more conditions. For instance, if you're young, your stroke risk goes all the way down. But the point is that thing it's better than the current what they're using in hospitals, the Chads2 score. And then there's an improvement in the Chads2 score called Chads2 VASC for prediction. But the thing is, that's just as simple as the as the models that they're currently using. It's just more accurate, okay? Because it was built from much more data and really built from that data. But I think the fundamental point here in this section is that I want to see interpretability considered to be one of the fundamental desirable qualities in a predictive model. There are not that many people designing interpretable predictive models, and I think that's important. Great. So actually, yeah, that's it for me. So thank you very much.
We have time for a few questions. Your phone, too.
Okay, so my question is, for the first study, the energy, do you guys do anything to the model, or does the city take the result of the model and decide to do something to the high-risk manholes or something like that?
Yeah, that's a really good question. So Con Edison has this inspection program, and they want to do a couple things with our tools. So the first one is figure out how often they need to inspect manholes. And there's currently a mandate by the Public Service Commission that they have to inspect every 5 years. So what we've been providing for them is if we can actually use the reactive point processes to simulate into the future and then enact different inspection policies and give them like a cost-benefit analysis for different types of inspection policies. So that's one thing that they're using our tools for. Also, there's a vented manhole cover program where they replace solid covers with vented covers that allow gases to escape and reduce the probability of an event. So we've been trying to help them figure out how to, which manholes need cover replacements, like how to do that in a cost-effective way. And then also, we have a lot of tools that provide case studies of manholes. Like you can give it the number of a manhole, and it'll give you this whole, it's like a report card for the manhole. And then they can use that to figure out whether that manhole should be inspected and with what priority. Yeah. Thank you.
Hi, thanks. That was very interesting. I have a question about the last model. So there's interpretability, like you talked about, and there's accuracy, but there's also clinical utility. And so in people who've had previous strokes, that's a population where you already know that they're going to have strokes. Did you try to do a predictive model of people who didn't have strokes and then see what came out? Because your first 2 or 3 predictors were prior strokes, prior TIA.
Yeah, so we haven't. So we've been just working on the problem that, just to beat the Chads2 score, essentially, at what it's designed to do. So we've done that. But it's definitely not difficult to take the tools that we've designed and design a specialized, version of whatever scoring system you want if you have the right data. So for instance, with the data we have now, I could talk to you and find out exactly what you mean, and then we could actually do that. And it wouldn't take long. Yeah.
Hi, thanks for the talk. I actually have a follow-up question to the last application you talked. Well, you have much more data points for the model, as you showed in example. So, well, I think it's, you would assume you will make a better prediction. I was just wondering, if you reduced your data points to the 1700, similar to what the original score is designed for, what kind of performance would this give?
So we don't have access to that data, the data that they originally designed the study for. So we measure predictive performance using cross-validation. So in our paper, we actually have ROC curves for the different models. So you can actually see the quality of the predictions that have been cross-validated, and they're on a test set. So it's not a matter of the size of the data set that we used. It's really cross-validation out-of-sample performance we care about.
Hi there. I have a rather less technical question, and that is, it seems that what you're doing is rare event prediction when you talk about manhole covers blowing. Does it have other applications like national security applications? I know you've done some research on crime data. Could you find a terrorist if you had enough information?
Smoking.
So I don't know if I can find a terrorist because I've never worked with terrorist data, but I do know that I can find criminals in Cambridge because I have worked with that data. So that it's a good question. The methods that we're using, it's what we've developed is a knowledge discovery framework, right? So it's the pipeline that was discussed in the morning section where you have to essentially become a domain expert yourself. You prepare the data, you visualize, all this kind of stuff. What I'm showing you here are examples of that pipeline in action. Yeah.
Quick question on is it okay? Yeah, quick question on interpretability. There's a class of models such as these where these rule-based approaches are really elegant. What are your thoughts on finding interpretability in models that consist of just the vast numbers of numerical parameters, the kinds of things that we're seeing in deep learning, where we have effectively the model is millions and millions of coefficients, and we would like to have some insight into those. And I'm not sure if this rule-based approach is going to apply there, and I'm wondering what your thoughts are.
I think it probably just depends on the application. I mean, I can't tell you in advance whether a particular approach is going to work the best for a particular application, but I think it's definitely worth trying. If you're going to try all the other standard methods, you're going to try your conventional toolbox of your decision trees and your this and your that. And why not try something like this where it's actually designed to do interpretability, right? I guess that's the point, yeah.
Thank you.
Thanks.